Next thing we're going to look at is what mathematics we're going to use for these waves on a string. And the two equations we need to use are the wave equation, solve for the frequency, and we know the velocity has to do with, again, the tension of the wire and the thickness of the wire. So let's look at the string. So what does a wave look like? Is a wave one wavelength up and down. This is equal to lambda. So if we look at this string, it looks like one wave. So in this particular one, we have lambda is equal to L because we have one full wave on that string. Then what happens if we look at just half of it? If we have it like jump rope style, where we have an antinode in the middle and nodes on either end, because again, these ends are fixed, then we would imagine that this could continue to another half of the wave. If the string was longer, we would have a longer wavelength. So basically we say that the length is equal to half of a lambda. And so lambda for this harmonic is 2L. And since this is the longest wave we can get onto our string, because we have to have both ends fixed, this is going to be called the first harmonic. Then what happens if we make it shorter? So we vibrate a little harder, we get a higher frequency, we're able to get more of a wave on here. And so again, we can imagine if this had another section, then this would be 1 lambda, and this is then a half of a lambda. So the whole thing together is 3/2 of lambda. And if we solve that for lambda, we get for the third harmonic that lambda 3 is equal to 2/3 over L. Now we want to be able to generalize this to a pattern and a single equation that we can use instead of having to examine one each time. So we figured out that the first harmonic up here, that is basically it's half of lambda. So lambda is equal to 2L. That's the length of the, if we had a wire twice as long, then lambda would be twice the length that we currently have. So we can generalize this to lambda is equal to 2 over 1 times L. And I know you're wondering why I put a 1 there because it's redundant, but you'll see. And then if we have our second harmonic is just equal to L, and so I'm going to write 1 as 2 over 2. And again, this 2 in the denominator is going to be important. And then the third harmonic is 2/3 L. And I get a 3 in the denominator. So I hope you see a pattern. We go from 1 to 2, 2 to 3, and what do you think is in that one? So it shouldn't be a surprise that it is in fact a 4 that goes into that equation there. So then we can make a generalized equation. We can put the lambda in with the frequency formula and figure out that we have a similar pattern here. We go from 1 to 2 to 3 to 4 if we want to calculate our frequency. And again, this is using the wave equation and the tension equation put together. So now we have two generalized formulas where we have the integer that we kept changing in the denominator here and the numerator here. We say that this has to be an integer of some sort, 1, 2, 3, etc. up to infinity. Now it's only going to be really practical to put certain wavelengths on that wave, but generally we should be able to go up to infinity as we get higher and higher frequencies. So what these frequencies are called a harmonic series. That these are the frequencies that string or wire or cord likes to vibrate. So F1 is called the fundamental harmonic, and F2 is called the second harmonic. And so anything but these harmonics are quickly damped out, and so they don't last long. These are where the string likes to be. So the harmonic is the term that we're typically going to use, but in music they also use the term overtone, and it's basically just shifted up one. So we're generally going to use harmonic, but the first harmonic is the fundamental frequency, and then the second harmonic is called the first overtone. Okay, so let's give this a try. Which picture represents the third harmonic? And in the next section here, we're going to do some math. So which one represents the third harmonic? Well, the third harmonic is right here. So this represents the third harmonic, and we can tell it's the third harmonic because there are 3 antinodes. 3 antinodes. Or if we wanted to go with counting the nodes, there are 1, 2, 3, 4 antinodes. So for a harmonic, there's n plus 1 nodes.